topic of this presentation is 5G quality of service, the impact of security functions on latency. This is a collaboration between my colleagues Johannes Naab and Georg Kalle from the Technical University of Munich and Iris Adam from Nokia Bell Labs Munich. In this talk, we consider a very special type of communication in 5G networks, the ultra-reliable low-latency communication, or short ULLC. ULLC means that 99.99% of all packets successfully arrive at their destination, and they do this with a possibly low latency. Low latency in our context means that we have a maximum latency of 1 millisecond. This delay is measured one way, end to end, and we only consider the radio access network for our to test if these ULLC requirements are even possible to handle in network function. We create our own virtualized network function scenario. Therefore, we use Linux and KVM as a hypervisor. And for the network function, we choose an intrusion prevention system. In our case, we use NOMS'20, but we deactivate the entire rule set of this intrusion prevention system, turning the intrusion prevention system in a basic forwarder. So it simply accepts all the packets, forwards it to another port, and sends them out again without any real processing happening on the packets. And the latency which we measure is only measured between the egress and the ingress interface of this network function, so we don't consider any other network delays. The results of our measurements are shown in this table. So what you can see here is that up to the 99.9th percentile, everything is fine. So we stay well below our 1 millisecond goal. However, if we consider higher percentiles, so 4 nines or even 5 nines, we can see that our latency goal is seriously violated. If we have an even closer look at our measurements, so here we can see in this plot that the measurements happened over a measurement time of 30 seconds. And even for this short measurement window, we see several of these latency spikes. So we have several violations of our ULLC deployment. So what are the reasons for this system behavior? One of the main reasons for the poor latency behavior, which we saw in our initial example, is the interrupt-based I/O of Linux. There, newly arriving packets can cause interrupts for currently running processes, which then lead to the delay which we saw. We can also have several CPU features which may cause these unwanted delay spikes, one of them being the dynamic scheduling of processes onto CPU cores. So if applications or processes need to switch from one CPU core to another, this may lead to unwanted delays. We can also have virtual cores, which then share a common physical core. If two processes use two different virtual cores, which then lead to resource contention on the physical core, this may lead again to unwanted delays between them. We can also save some energy on nowadays CPUs by using certain energy saving mechanisms. However, if we switch between different operational states on the CPU using these energy saving mechanisms, this may again then lead to additional delays when switching between them. And another important reason is dynamic cache allocation. This means that if two processes use the same amount or the same portion of the last level cache, this again leads to resource contention then for the last level cache, which then causes unwanted delays. And another important reason, especially for virtualized environments, are the high and quite inconsistent costs when copying packets from a network card into the virtual machine and back. So what can we do to fix these issues? One of them is switching from an interrupt-based I/O to a polling-based I/O. We can do this using specialized frameworks. For instance, the Intel Data Plane Development Kit. There, an application can now decide when to receive new packets, and this leads to a more consistent latency behavior because we can predict when to receive new packets. We can also use our CPU features differently. We can, for instance, statically bind CPU processes onto cores to avoid any costs when switching between CPU cores. We can disable the virtual cores entirely. This lowers performance but creates a more consistent performance for the remaining cores. We can also disable energy saving mechanisms, raising energy costs, but providing a more consistent latency behavior. And we can finally use a tool called IntelCat. This stands for Cache Allocation Tool, which then binds statically cache to cores, and then we can avoid unwanted resource sharing between processes on the CPU cache. And last but not least, we can finally use an acceleration feature of network cards called single root I/O virtualization, which basically means that we have a more consistent performance when copying packets from network cards into VMs and back. How this looks on our real system is depicted in this picture. Here we can see the 4-core CPUs of our host system. We configured the operating system of the host system to run exclusively on P-core 0 and isolate all other cores. We can then use 2 of these isolated cores to host a virtual machine. There we do the same thing again. We exclusively bind our operating system to 1 core, which then leaves the P-core 2 isolated from both host system and VM system. There we host our network packet processing application. We use again the single root I/O virtualization feature. This means we can bind a certain portion of the network card exclusively to P-core 2, and this then leads to a more or less direct path from our application down to the network card, which is not influenced by either the host operating system or the virtual machine anymore. And this leads to a more, or should lead to a more or less consistent performance for our packet processing application. To test the performance of our previous system architecture, we use the following setup. So we have a load generator which creates our load and then again receives our load back from the device under test. The device under test is used to host our forwarding application, and then we included a third host called the timestamper, which uses passive optical taps to observe the packets running from the load generator to the device under test and back to the load generator. We use this timestamping facility to actually create hardware timestamping and to avoid any influence of the timestamping process on the actual traffic. For hardware, we use C&D processors, quad cores, 2.2 GHz, and we use Intel X557 NICs. For traffic, we use UDP, and we use DNS packets so that we can trigger certain rules on the intrusion prevention system, and we use constant bitrate traffic for our testing. For testing, we use actually 3 different configurations for our forwarder on the device under test with increasing complexity. So we use, as our basic example, the DPDK-based forwarder without snort. Then we use snort on top of DPDK as a forwarder. And then again, we activate the rule set on snort so that we create an actual intrusion prevention system. We measure these 3 forwarders again in 2 different deployments. One deployment being the bare metal deployment and the virtualized deployment then in a virtual machine, so that we can determine the costs between hardware and virtual deployment. This measurement plot shows the DPDK-based forwarder. The plot on the y-axis shows the latency, and on the x-axis shows the actual percentiles which we measured. It also shows in orange the VM deployment and in blue the hardware deployment, and the different lines symbolize different throughput rates at which we measured. What we can see from this measurement is that performance is there's a slight performance difference between hardware and virtualized deployment, but it's roughly 4 microsecond difference, so it's not that big of a difference, so we very well can host your LLC on bare metal and virtualized system. And what we can also see is that the actual throughput rate does not make that big of a difference in this scenario. However, the scenario actually changes if we switch to the SNOT-based forwarder. Here we can see that throughput actually can make a difference. So if you switch from 80,000 packets per second to 90,000 packets per second, we can actually see that the latency raises above our 1 millisecond goal, which we see symbolized in this red line. However, if we do not overload our system, system performance or latency performance still is very well below our 1 millisecond goal. Again, keep in mind log scale, so we stay far away from our overload point if we have a rate of 80,000 packets per second. If we then activate the rule set on Snort, performance actually changes a little bit. So what we can see here again is the red line. However, the switch between non-overloaded system and overloaded system state is not 80 to 90,000 packets any longer, but 60 to 70,000 packets per second. So if we activate our rule set, it's actually better to stay on 60,000 packets per second, then we will always keep our 1 millisecond goal, at least for the percentiles which we observed here. Okay, so these were the measurements for the latency. The next measurements take a more detailed look on the tail latencies, which we saw on the previous measurements. For this, we focus on the DBDK based forwarder because it was the most stable, and therefore we can observe the input-output in the cleanest way possible. So what we can see over our measurement is a very regular pattern. So here you can see our 30-second measurement period and the latencies on the y-axis. And what you can see is that latencies seem to happen in a very regular shape along these diagonal axes. I cannot go too much into detail why these diagonal shapes happen. I have to refer you to the paper. There it's explained in a little bit more detail. The shortest explanation I can give here is that we have a test traffic which actually undersamples the interrupts of the OS. So what you can see here, or the root cause of this diagonal pattern, is the interrupts of the OS where the packet processing application runs. These OS interrupts have different lengths, so we have actually two different interrupts happening. One has a maximum of around 10 microseconds. This is what you can see in these lower diagonal lines, and we also have these higher diagonal lines. These are the interrupts which have a runtime of roughly 13 microseconds. If we, so this is the measurement based on the bare metal deployment. We can also have a look at the virtualized deployment, and there we can see basically that the amount of diagonal line doubles, and the explanation for that is that we don't have one OS running, but we have actually two OSs running, both performing their own interrupts. These interrupts in the VM case again take also additional time, so this is one of the reasons why the virtual machine latency is slightly higher than the measurements on the bare metal system. What can we now do with these previous measurements? So what we saw is that it's a very bad idea to actually overload our system, and that it would be good to have some kind of prediction mechanisms where we can actually predict when the system will overload, and then we can also try to avoid these overload cases so that we can keep our ULC quality of service agreements. So therefore we have a very high-level overview of our system architecture. So we receive a packet on the network card, then it goes via direct memory access to RAM, and from there via the memory bus to the CPU. So we actually have two phases. We have the transfer phase, we call it. So this is the phase where the packet travels through the system, which we cannot influence that much. And then we have the second component. This is called TApp. This is the application runtime. So this is what we actually can influence in software. So what we also know from previous work is that not the transfer time is the problem, but the application time. So TApp is what actually determines the capacity of our system. So if that portion of the system overloads, the entire packet process or the entire latency of our packet processing application will spike to these high values. So how can we determine how much our capacity for a TApp is? So what we get from our measurement is not the application component, but we measure the entire thing. So we measure the end-to-end. So we need to determine how high our T-transfer is. But what we also know from our previous measurements is that the DBDK forwarder, the basic or most basic example that we have, actually has no real processing delay, because the application basically does nothing except for receiving and sending out packets almost instantly. So we can use this DBDK layer 2 forward example as an approximation for our tree transfer. We now have our T end-to-end and then can calculate TApp for our snort scenarios. What we also know from our previous measurements is that not only the packet processing application is hosted, but we also need to spend some CPU time on interrupt processing. However, we can calculate this time spent on interrupts from our interrupt rates and interrupt execution times. So if we now want to compute what our system is actually able to calculate during 1 second is, we take our capacity. So we have a calculation time of 1 second. Therefore, from there, we need to deduct the time for interrupt processing, because we need to spend the time on interrupt processing anyways. And what is remaining, we can now divide by the cost of each packet, and then we get our maximum rate. We actually applied this model to our previous measurements, and then we get the values which are shown in this first column of this table. So we get different rates for the hardware snort forwarding scenario and for the snort filtering scenario accordingly. And what we can see from the measured rates is that the measured rate actually predicts, or we predicted that system capacity is below 90,000, and our model roughly creates corresponding numbers. So this very rough model is a very conservative approximation. So there are actually effects which may lead to a slightly more efficient processing at higher rates, which our model simply ignores. So the real maximum capacity is slightly higher than what is predicted by our model. This is not that bad, because you should always have kind of a safety margin when creating such systems to really avoid the overload at any cost. What is quite nice about this model is that we require a low number of input parameters, so we just need the median latency. This is what we get from our basic forwarding scenario. Then we need the median latency of the investigated scenario that we can calculate, and again we need the interrupt processing time of the operating systems. And this is all which we need to create a maximum predicted rate. Before actually concluding my talk, I want to give a short notice about the reproducibility which we tried to achieve for this paper. So everything which we tested in this paper, so all the software, all the measurement tools, all the test script and the experiment scripts are all available on GitHub. So I created a short GitHub page where you can see actually how we did it, and the entire script which created our measurements are hosted there. And you can also get the entire measurement data, so from pcaps up to the data which is then used in the plots. So if you're interested, just follow these two links and you'll get to the data. So, and now the contribution of our talk. Our goal was to have a 1 millisecond goal, which includes the entire run. So what we presented in this talk are only measurements of a little piece of this entire run. So we should not consider 1 millisecond being our goal, but for the network function actually a little bit less of time is available. So related work suggests to not consider 1 millisecond as the goal for network functions, but consider even stricter goal of around 350 microseconds. So, but even if we consider this very strict 350 microseconds goal, we can still say that our system is able to achieve that. So the worst case latency which we actually measured for the 5.9 percentile is 114.7 microseconds for the most demanding snort filter scenario which we investigated. So good news. URLC is possible on these systems. So we only used off-the-shelf hardware. And if we configure the software which runs on it correctly, we can totally achieve this. So this is a very good news. We can also present a model that is able to predict the performance of such a system, which comes in very handy when trying to avoid overload on this system. However, we have also detected some limitations. So one of the limitations for this system is that the static allocation of CPU cores increases the costs of these systems, because we cannot host an arbitrary number or a very high number of VMs on these systems any longer, but only a very limited amount, because we only have to statically allocate the CPUs to the VMs, and then we cannot change this static allocation any longer without shutting down VMs and starting new ones. So this raises costs, but we also include in our paper some more measurements. So what we investigated but didn't have the time in the presentation is bursts. So if several packets arrive back to back at our network function, this may lead to short time overloads. So if you're interested in measurements of these kinds, please have a look at our paper. And we also, I just briefly mentioned that energy costs will rise. We actually created some measurements. So the worst case was we raised energy consumption by 50%, but depending on the concrete scenario, so if you have more active or more idling systems, this energy consumption can, or these more costs of energy consumption can also go down to roughly 4%. If you're interested in that, please also have a look at the paper. So now, thanks for listening.